Universe. Physical properties. Of the four fundamental interactions, gravitation is dominant at astronomical length scales. Gravity's effects are cumulative. By contrast, the effects of positive and negative charges tend to cancel one another, making electromagnetism relatively insignificant on astronomical length scales. The remaining two interactions, the weak and strong nuclear forces, decline very rapidly with distance. Their effects are confined mainly to subatomic length scales. The universe appears to have much more matter than antimatter, an asymmetry possibly related to a CP violation. This imbalance between matter and antimatter is partially responsible for the existence of all matter existing today, since matter and antimatter, if equally produced in the Big Bang, would have completely annihilated each other and left only photons as a result of their interactions. The universe also appears to have neither net momentum nor angular momentum, which follows accepted physical laws if the universe is finite. These laws are the Gauss laws and the non-divergence of the stress-energy momentum pseudotensor. Size and regions. The size of the universe is somewhat difficult to define. According to the general theory of relativity, far regions of space may never interact with ours, even in the lifetime of the universe, due to the finite speed of light and ongoing expansion of space. For example, radio messages sent from Earth may never reach some regions of space, even if the universe were to exist forever. Space may expand faster than light can traverse it. Distant regions of space are assumed to exist and to be part of reality as much as we are, even though we may never interact with them. The spatial region that we can affect and be affected by is the observable universe. The observable universe depends on the location of the observer. By traveling, an observer can come into contact with a greater region of spacetime than an observer who remains still. Nevertheless, even the most rapid traveler will not be able to interact with all of space. Typically, the observable universe is taken to mean the portion of the universe that is observable from our vantage point in the Milky Way. The proper distance, the distance as it would be measured at a specific time, including the present, between Earth and the edge of the observable universe, is 14 billion light-years, or 14 billion parsecs, making the diameter of the observable universe about 93 billion light-years, or 28 billion parsecs. The distance the light from the edge of the observable universe has traveled is very close to the age of the universe times the speed of light, 13.8 billion years. But this does not represent the distance at any given time, because the edge of the observable universe and the Earth have since moved further apart. For comparison, the diameter of a typical galaxy is 30,000 light-years, and the typical distance between two neighboring galaxies is 3 million light-years. As an example, the Milky Way is roughly 100,000 to 180,000 light-years in diameter, and the nearest sister galaxy to the Milky Way, the Andromeda Galaxy, is located roughly 2.5 million light-years away. Because we cannot observe space beyond the edge of the observable universe, it is unknown whether the size of the universe in its totality is finite or infinite. Estimates for the total size of the universe, if finite, reach as high as 10 to the 10 to the 10 to the 122 megaparsecs, implied by one resolution of the no-boundary proposal. Age and expansion. Astronomers calculate the age of the universe by assuming that the lambda CDM model accurately describes the evolution of the universe in a very uniform, hot, dense, primordial state to its present state, and measuring the cosmological parameters which constitute the model. This model is well understood theoretically and supported by recent high-precision astronomical observations such as the WMAP and Planck. Commonly, the set of observations filtered include the cosmic microwave background, the brightness redshift relation, for a Type 1a supernova, and large-scale galaxy clustering, including the baryon acoustic oscillation feature. Other observations, such as the Hubble constant, the abundance of galaxy clusters, weak gravitational lensing, and globular cluster ages, are generally consistent with these, providing a check of the model, but are less accurately measured at the present. Assuming that the lambda CDM model is correct, the measurements of the parameters using a variety of techniques by numerous experiments yield a best value of the age of the universe as of 2015 of 13.799 plus or minus 0.021 billion years. Over time, the universe and its contents have evolved. For example, the relative population of quasars and galaxies has changed, and space itself has expanded. Due to this expansion, scientists on Earth can observe the light from a galaxy 30 billion light-years away, even though that light has traveled for only 13 billion years. The very space between them has expanded. This expansion is consistent with the observation that the light from distant galaxies has been redshifted. The photons emitted have been stretched to longer wavelengths and lower frequencies during their journey. Analyses of Type 1a supernova indicate that the spatial expansion is accelerating. The more matter there is in the universe, the stronger the mutual gravitational pull of the matter. If the universe were too dense, then it would recollapse into a gravitational singularity. However, if the universe contained too little matter, then the self-gravity would be too weak for astronomical structures, like galaxies or planets, to form. Since the Big Bang, the universe has expanded monotonically. Perhaps unsurprisingly, our universe has just the right mass-energy density, equivalent to about 5 protons per cubic meter, which has allowed it to expand for the last 13.8 billion years, giving time to form the universe as observed today. There are dynamical forces acting on particles in the universe which affect the expansion rate. Before 1998, it was expected that the expansion rate would be decreasing as time went on due to the influence of gravitational interactions in the universe, and thus there would be an additional observable quantity of the universe called the deceleration parameter, which most cosmologists expected to be positive and related to the matter density of the universe. In 1998, the deceleration parameter was measured by 2 different groups to be negative, approximately negative 0.55, which technically implies that the second derivative of the cosmic scale factor has been positive in the last 5 to 6 billion years. This acceleration does not, however, imply that the Hubble parameter is currently increasing. See deceleration parameter for details. Spacetime. Spacetimes are the arenas in which all physical events take place. The basic element of spacetimes are events. In any given spacetime, an event is defined as a unique position at a unique time. A spacetime is the union of all events in the same way that a line is the union of all its points, formally organized into a manifold. The universe appears to be smooth spacetime continuum consisting of 3 spatial dimensions and 1 temporal dimension, time. On average, space is observed to be very nearly flat, with a curvature close to 0, meaning that Euclidean geometry is empirically true at high accuracy throughout most of the universe. Spacetime also appears to have a simply connected topology, in analogy with the sphere, at least on the length scale of the observable universe. However, present observations cannot exclude possibilities that the universe has more dimensions, which is postulated by theories such as string theory, and that its spacetime may have a multiply connected global topology, in analogy with a cylindrical or toroidal topologies of 2-dimensional spaces. The spacetime of the universe is usually interpreted from a Euclidean perspective, with space consisting of 3 dimensions, and time consisting of 1 dimension, i.e. the 4th dimension. By combining space and time into a single manifold called Minkowski space, physicists have simplified a large number of physical theories, as well as described in a more uniform way the workings of the universe at both supergalactic and subatomic levels. Space-time events are not absolutely defined spatially and temporally, but rather are known to be relative to the motion of an observer. Minkowski space approximates the universe without gravity. General relativity describes space-time with matter and gravity. Shape. General relativity describes how space-time is curved and bent by mass and energy, gravity. The topology or geometry of the universe includes both local geometry in the observable universe and global geometry. Cosmologists often work with a given space-like slice of spacetime, called the Comoving Coordinates. The section of spacetime which can be observed is the backward light cone, which delimits the cosmological horizon. The cosmological horizon, also called the particle horizon or the light horizon, is the maximum distance from which particles can have traveled to the observer in the age of the universe. This horizon represents the boundary between the observable and the non-observable regions of the universe. The existence, properties, and significance of a cosmological horizon depend on particular cosmological model. An important parameter determining the future evolution of the universal theory is the density parameter, omega, defined as the average matter density of the universe divided by a critical value of that density. This selects one of 3 possible geometries depending on whether omega is equal to, less than, or greater than 1. They are called, respectively, the flat, open, and closed universes. Observations, including the Cosmic Background Explorer and Planck maps of the CMB, suggest that the universe is infinite in extent, with a finite age. These models thus support inflationary models and the standard model of cosmology, describing a flat, homogeneous universe presently dominated by dark matter and dark energy. Support of life. The universe may be fine-tuned. The fine-tuned universe hypothesis is the proposition that the conditions that allow the existence of observable life in the universe can only occur when certain fundamental physical constants lie within a very narrow range of values. So that if any of these several fundamental constants were only slightly different, the universe would have been unlikely to be conducive to the establishment and development of matter, astronomical structures, elemental diversity, or life as it is currently understood. The proposition is discussed among philosophers, scientists, theologians, and proponents of creationism.